two aspects. The first one is the energy, and the other one is matter, or you can say material. Now, if you look into the universe, you find that there are abundance of the material with diverse characteristic and diverse constituents, which is making our universe. Interestingly, whichever material that exists in the universe is made up of an element that belongs to our periodic table. And now we have some 100 plus elements, and if you mix them in different proportions, you can make compounds which are infinite in number. So we have a very diverse world of material. And when we say we will going to study about materials in this subject, it is impossible to cover such a diversified, distributed category of the system that exists. So when I say we will going to study engineering materials, we are restricting ourselves to a subclass of the materials world. So what exactly we mean by the term engineering material? Engineering material means anything an engineer will going to use in his or her profession. So it's a very general, crude definition of looking at an engineer. Now, if you say I am a computer engineer, then the materials which I require is drastically different from if I define myself to be a civil engineer or a mechanical engineer. So depending on the engineering branch, you still have a restricted class of engineering material that you will going to use. For example, for an electronics engineer, an IC or a chip is the most important material. Compared to that, if you are a civil engineer, you may be most interested in the concrete or maybe steel. Likewise, if you are mechanical engineer, your major interest might be in the materials that goes into the making of, say, an automobile engine, and so on and so forth. So even if I define a material to be an engineering material which an engineer will going to use in his or her profession, it will still be a very vast category. Therefore, in a course of a one particular semester, it is not possible to cover all such engineering materials which different branches of engineers will going to use in their profession. So what we will do is, instead of studying all such engineering materials independently, we will try to classify engineering materials into certain general subgroups or subclasses, and then we will study them as a particular class. So the question is, now how will you going to classify engineering materials? There are variety of ways by which you can classify engineering materials into subclasses. For example, if you remember your school days, the most primary classification scheme which we used for the classification of materials was based on its physical state. Say we used to classify materials like the solid material, the liquid material, and the gaseous material. So that was one way to classify material. The another interesting variant with which we have classified engineering materials or materials in general in our school days was depending on its electrical properties. So we used to classify materials to be conductor, semiconductor, or insulator. Likewise, if you look at the magnetic properties of the material, you can say material is either magnetic or non-magnetic. And then within the magnetic class, you might have heard that something is called ferromagnetic, something is called paramagnetic, something is called diamagnetic, and so on and so forth. So my point is, there are variety of ways by which you can classify the engineering materials or materials in general. So what will be our approach of classification? We will going to classify engineering materials into subclasses by following two different approaches. In the first approach, we will classify engineering materials based on their internal characteristic. Based on this, we have primarily three major subclasses of the engineering materials. The first major class is referred as metals and alloys. Metals, all of us are familiar with, so I need not to define whom I am referring as metals. Alloy, although we have heard about alloys since long now, but still couple of students might have some confusion about the term alloy. So the crude or the primary definition of an alloy is, you can call alloy to be a mixture of two or more metals. So basically the first class, metal and alloys, is basically a metal class. Either metal as an independent entity, an independent element, or you have mixture of multiple metals, which is an alloy. Now when I refer alloy to be mixture of metals, you have to put a condition on the way you will going to mix these metals. The metal always have to be a homogeneous mixture. If it is homogeneous mixture at atomic scale, only then we call that mixture as alloy. If it is not homogeneous mixture, then what will be that situation? We'll come back to that at a later stage. So the first category or first class of the engineering materials is the one where you have the solid, which is either belong to an elemental metal, that is single component, or mixture of metals homogeneously, which is alloy. Couple of examples: metals like aluminium, copper, gold, silver, brass, or mixture of metals like bronze, steel, or magnetic alloys. So all of them are very important engineering materials, and in general we will talk about the properties of metals and alloys class together with couple of example problems where I will going to refer a specific material. Then the second broader category of engineering material is called ceramics and glasses. Now what exactly the ceramics are? Ceramic is also a term which we had been exposed to during our primary studies. So in general, ceramic is basically a metal oxide. You know that metals are conducting, but ceramics are both electrically and thermally insulating. So wherever you need an insulation characteristic, we used to have a ceramic material. The most common ceramic which everybody uses is either the floor tiling, or you can say the window glasses. They are all metal oxides. So the easiest way to look at the ceramics is every metal oxide belongs to this particular class. A more concrete definition of ceramic is, this is the class of metal oxides which pertains high melting point, high boiling point. They are electrically and thermally resistant. A couple of examples could be silica, soda lime glass, which is also the window glass. We also call the soda lime glass as the window glass. The concrete, the structure of the concrete is also metal oxide, so it belongs to the ceramic class. Cement, alumina, which is aluminum oxide, a very commonly used chemical compound to make high temperature materials. Silicon carbide, this is also a very important category of ceramic material that can withstand to very large temperature as high as 4000 degrees centigrades, and it is also very hard. So when it comes to make cutting tools, generally the carbides are being used. Ceramics and glasses could be crystalline or it could be amorphous. Now, sorry for the disruption. We had some connectivity issue because of which we have lost the connectivity for a couple of moments. We continue our discussion. We were discussing the ceramic and the glass category of the engineering materials, and what I was telling was the ceramics and glasses could be crystalline or the non-crystalline material. So the fundamental difference in general between the ceramics and glasses are ceramics could be crystalline or non-crystalline, while the glasses are always non-crystalline, or you can say amorphous. The third category of engineering material is also very important, and this belongs to the category of organic materials. We call them organic polymers, or you can call them in general the polymeric materials. Polymers, you people know, they are the long chain hydrocarbons. So they are made up of carbon and hydrogen primarily, and their physical structure is in the form of a long carbon chain. And depending on the carbon chain length, we have different types of polymers. Couple of important polymers that we use is the plastic, something like PVC or polyethylene. We also use polymers in the fibrous form like nylon, terylene, or another important class is the rubbers. Rubber could be natural or it could be synthetic. So over the course of the discussion, we will refer these three major class broadly, and as and when required as a specific problem or an example, we will refer to a special material belonging to either of these class. Now, despite of such vast variety of the materials that exist, engineers are still looking for more and newer materials which gives superior properties as compared to the individual class offering us. Say for example, metals normally are malleable, means you can shape them very easily. But the disadvantage is normally metals have relatively lower melting point. So as an engineer, let's say you want to design a material which is easily malleable, but its melting point should also be high, then you have to create a hybrid material which is made up of one element that belongs to the metal and alloy class and the other element that belongs to the ceramics and glass category. So likewise, making a hybrid material out of two or more classes gives you a new hybrid materials which possess superior properties as compared to the individual classes. Couple of important example materials I have mentioned here. For example, if you create a hybrid of metal and ceramic class, you can have a material, something called boride reinforced steel. You might have heard this term. This is the reinforced steel that is being used in the construction of structures like houses, and this steel, because of the presence of the boron, do not corrode. The general steel easily gets corrode, but if you put a boron into this steel, means you reinforce boron into the steel, the product that you get do not corrode over a period of time. Likewise, if you create a hybrid between metal and polymers, you get metal reinforced plastics. These plastics has very low density, means they are very light in their weight, but their mechanical behavior is as good as any metals. With metal reinforced plastic, you can create bonnets of automobiles with which you can reduce its mass, and in that way you can improve the fuel efficiency. Likewise, if I take one component from ceramic and other one from the polymer class, I can have glass fiber reinforced plastic, and this is again a very lightweight material, but its mechanical strength is extremely high, and with this you can create materials which is very light, but its mechanical strength is extremely high. Generally, this category of material is being used to make high-speed boats and bullet shields. So this is one approach of classification. The another approach of classification that we will frequently use is based on the application of the engineering material, where you will going to apply the engineering material. Based on this, we can categorize engineering materials into three subclasses, namely the structure, the machines, and the devices. Any material that goes into the design and making of a structure are belong to the structural class of material. For example, concrete or a furnace or a bridge goes into the making of a structural entity, so they belongs to the structural class. Likewise, if your object has a moving part, then it refers to a machine, and you can have motors or generators as an example to this particular class of material. The third class, based on the applications of the engineering material called device, is a relatively new class. In this category of material, we have semiconductor devices like transistors, lasers, magnets, cells, or all kind of sensors belonging to this particular class. So all your electronic devices is basically belonging to this particular class. So in different instances, either we talk about the three broader class of the material or the three subclass of the material based on the applications, and we will going to study these materials as the subclasses based on either the properties or based on the applications. In this particular slide, I am going to define two terms, materials engineering and materials science. You will frequently heard these two terms. So at this point in time, you should be able to understand the difference between the two. Material science is basically a subclass of science in which an engineer investigates the relationship between structure and properties. So how the structure affects the property, or how the property can be achieved by modifying the structure. If you are studying the relationship between structure and property, the science that you are dealing with is called the material science. While in materials engineering, you are designing the structure to achieve specific properties of the material. So we will learn ways and means of modifying the structure so that I can also modify the properties. So in this particular course, we will going to make correlation between this tetrahedron, where you have four components, namely the structure, the properties, the performance, and processings. All these four terms are strongly correlated. Say, if you change the structure, you can alter the properties, and if you are altering the properties, you can alter the performance. Now, how can you change the structure? To change the structure of the material, you need to alter the processing condition. So there are two different ways of approaching to a design problem. For example, you are designing, let's say, a boiler. Then your client will give you the performance parameter which your product should meet to. So you start with the performance parameter. Now, once the performance parameters are known, you will define materials properties which is required to meet those performance parameters. So from the design parameters, you come to the properties. Now to fulfill those properties, you need to identify the required material, or rather you need to identify the required structure which can meet those properties. And once you define the structure, you need to define the processing conditions with which one can achieve that structure. So there is a strong correlation between performance, properties, structure, and processing. So this is one way of approaching to a design problem. Another one is, let's say you have a manufacturing plant. So you have a couple of machines in your plant with which you can process a material. Means your processing conditions are now well defined. So once the processing conditions are well defined, you know what kind of structures you can produce in your plant. So with the processing conditions, now you have a limitation on the structures that you can make, and with those structures, what kind of properties that you can produce is also now known. Since now the properties are known, you can classify or define the performance which you can achieve out of your product. So either you go with the forward approach or you go with the reverse approach. In most of the industry, the forward approach is being followed, which is you start from the processing and end up to the performance. For most of the category of the engineering products, this works fine. But if you are working on a very challenging problem, let's say you are designing a rocket or maybe a missile, which is kind of a very complex problem, then you cannot use this forward approach. The other, you have to do the reverse engineering, means you have to first define your performance parameter, and then from that performance parameter, you will go back to the processing condition, and if it is not available in your plant, you will establish those. So depending on the requirement, you can either follow the forward approach or the reverse approach. In this particular course, as a materials engineer, we will going to study different materials class with a focus on their properties, which are the following ones. The mechanical properties, where our focus will be on elasticity and stiffness, the plasticity, strength, brittleness and toughness, and fatigue. Most of the terms you people are familiar with. If you are not, I advise you to refresh your understanding about these terms. We will frequently refer to these particular terms in our course of the study. Then we will talk about the electrical properties of the material, where the focus will be on electrical conductivity and resistivity. We will discuss the dielectric properties of the material. You know, the dielectric materials are the one that goes in the manufacturing of your capacitors. To define any dielectric, the important physical parameters are their polarizability, their capacitance, the ferroelectric, piezoelectric, and the pyroelectric properties. What are these properties? We will going to study them in detail when we talk about the dielectric class of the materials in our 5th unit. Then the magnetic class of the materials, where 3 important characteristics: paramagnetic properties, the diamagnetic properties, and the ferromagnetic properties will be important, and we will talk about them. As far as the optical properties are concerned, the refractive index, the material's ability to either absorb, reflect, or transmit light, and the phenomena of double refraction, which is also called birefringence, which you have studied in your first course in physics, where one beam, when passed through a material, gets split into 2 beams, is important. In this course, we will not going to study the optical properties of the material, so you can exclude optical properties from the discussion. As far as the chemical properties are concerned, our only focus will be on corrosion. Of course, as a chemical engineer, you might have interest in many other properties, but from a general materials engineering perspective, we will focus only on the corrosion behavior of the material. As far as the biological properties of the material is concerned, the toxicity of the material to the biological entity is very, very important. Biocompatibility is another aspect which is also very, very important. But as a general course, we will not focus on the biological aspect of the material in this course. So when I say we will going to study engineering material, it is minus the optical properties minus the biological properties. And the materials that we will going to refer are all solids. So we are removing the gaseous class and the liquid class of the engineering materials. Why it is so? Because still we will have a very broad class. So for us, engineering materials are the ones which is solid only. Now moving to the next point, which is the structure of the engineering material. Now when I say structure, there are different ways with which you can define the structure of the material. The easiest one, the first one, is called the macrostructure. Macrostructure is basically the one that you see by an eye. For example, something is spherical or something is cubical or hexagonal. Seen through a naked eye, means the shape of the material, refers to the macrostructure. What you need to see a macrostructure? You can see it unaided, means you can see them with direct eye. The minimum typical resolution is of the order of a millimeter, or you can say fraction of a millimeter. So 10 to power minus 4 meter is the smallest possible resolution. That is the resolution limit of the human eye. The next level of the structure, which is very important and we will frequently refer, is called the microstructure, which you cannot see by eye, but if you put a material under an optical microscope, you can see the structure of the material. The typical resolution is fraction of a micrometer, and that is why the structure is called the microstructure. The typical resolution is 0.1 micrometer, or you can say 10 to power minus 7 meter. How magnified your material is at this stage? It is roughly 1500x, means you are zooming up to 1500 times. The next level is the substructure, means you are zooming the material higher and higher. With this, your magnification is like 10 to power 5 times, means you are zooming 1 lakh times. For such a zoom, you need an electron microscope, and with the electron microscope, you can see individual atomic layers. I will show you a couple of photographs how the microstructure looks like and how the substructure looks like. At this point, macro is the largest structure, followed by micro, followed by sub. At macro, you can see the entire material. At micro, you can see its surface in detail. At substructure, you can see individual atomic layers. Next in the category is called the crystal structure. You people have learned little a bit about crystal structure in your primary school days. If you forgot them, no need to worry. We will going to study crystal structures in more detailed manner. At this point, I define crystal structure to be a repetitive periodic block that makes the solid. And there are a couple of unique ways by which such repeatability dimension can be achieved. So we'll come back to the crystal structure more in detail. If you talk about its dimension, it is even smaller than the substructure. Next in category is the electronic structure that you have studied in your +2 in a very detailed manner. You talk about the electronic structure of the silicon, where you have a nucleus and surrounding orbiting electrons. So those kind of structure is now within the atom. So when you talk about the distribution of the electron around the nucleus, the structure that I am referring is electronic structure. Generally, you need spectroscopic studies if you want to study electronic structure of the material. The last in the category is now you are entering into the nucleus, and where you have proton and neutron distributed in a very tiny space. The way the proton and neutron gets distributed within the nucleus makes the nuclear structure. If you want to study a nuclear structure, the technique that one requires is called nuclear spectroscopic techniques, called NMR. Its full form is nuclear magnetic resonance. So macro is the largest structure, nuclear is the smallest structure. They have different degree of resolution, and you need different scientific tools to study this structure. In this particular course, our focus will be restricted to macrostructure, microstructure, substructure, crystal structure, and electronic structure. Nuclear structure we will exclude from our discussion, because in this course we will not going to study any radioactive material. Okay, I guess we are running out of time. So we'll stop here. In the next class, I will explain how, when you move from a macrostructure to a microstructure to a substructure, you find different interviewing information of the properties of the engineering material. So I will quote a couple of examples to drive my point that different structures gives you different information about the same material. So at this point, if you have any questions or queries, we have a couple of minutes left. I can quickly address them. You can post your queries if you have any at this point. Today also I kept the waiting room on for the entire session, but from the next class onwards, I will not going to do so. So please come within the 5 minutes of the scheduled time. Otherwise, you will be locked out of the session. Okay. LMS is still in the process of uploading. So if you have any issues with the LMS, please bear with us for a couple of days. Maybe within this week, you will get the first functional view of the LMS. But as far as the classes are concerned, you are receiving the link. So our classes will keep going on, irrespective whether the LMS link works or not. Okay, I'm going to the previous slide. Slides we are in the process of uploading. So most likely within this week, you will receive these videos, which are pre-recorded one. And I am also recording these live videos, whose link I will share with you. So you can download them from the Google. Yes, Akshita, you are asking something from this slide. As far as the tutorial class is concerned, teachers are not ready to take the tutorial classes. So your tutorials, if it is assigned to a teacher, it will be taken. TAs will start taking your tutorial classes and lab classes from the next week. All lab sessions will be conducted from the next week, not in this week. Akshita, no need. If you could not write something, anyways, I will going to share this video, so you can always play at your convenience. Today I will share both the links, so you can download and then you can study at your ease. Okay, so we are closing our today's session. You are supposed to move to your next class. So I'm closing our today's discussion.